Hello students, I hope you're all doing fine and have reviewed all the lectures that I have uploaded previously. In this lecture, we are going to discuss about the design of FIR filters by windowing. This is a very important lecture because FIR filter probably is the most uh, used filter as far as the digital signal processing applications are concerned, and it has very wide variety of applications. So this topic is extremely important to understand. In previous lecture, I gave you an introduction of digital filters, and then some introduction of FIR filter, its fundamentals, what FIR filter is, what is its mathematical model, and also gave you some introduction of the design methods. One of the methods that is used that we are going to discuss in this lecture as well. That method is called Fourier transform method, or it is most popularly known as windowing, in which we use different kind of windows to truncate the impulse response of the filter to make. So first I am going to spend some slides on the review of previous lecture in which we designed the low pass FIR filter. So design of low pass FIR filter using rectangular window function start with the desired frequency response, which is represented as HD of omega. So first thing that you do is to determine the mathematical representation of the required filter in ideal form. If you want to design a low pass filter, then this is how the ideal low pass filter's mathematical model look like. It has magnitude 1 as long as the frequency is between the cutoff frequency, and when the frequency is greater than cutoff frequency, it reads 0. So it has flat response when the frequency is less than cutoff frequency, and after cutoff frequency it is abruptly 0. It doesn't have any, it attenuates completely the input signal. So this kind of response is called brick wall response, and of course it is ideal. The real filter should look like the ideal response as much as possible. So the impulse response of this filter is given by this equation. We can find out this by simply taking the inverse Fourier transform of HD of omega. So inverse Fourier transform of HD of omega, or the impulse response HD of n, is given by this equation, which is basically a sinc function. We have already found how to find out this inverse Fourier transform in the last lecture. So it is basically a sinc function, a normalized sinc function, which looks like this. So the problem with this sinc function is that it has values, non-zero sample values for negative value of n, as you can see on the left side of the 0, and also it is infinite in length. So it is you can say, one problem is that it is infinite in length. So infinite length filter cannot be implemented practically. It would require infinite memory, to store infinite samples, which is impossible. And other problem with this is it has values for negative value of n. It means it would require foreknowledge, a future knowledge, which is not possible in real time. So it is non-causal, in other words. So therefore, because of this reason, it cannot be implemented practically. So ideal filter cannot be implemented practically. So what we need to do is we need to first make it causal as well as finite in length, so that we can implement it practically. So In order to do so, we need to clip the impulse response Sd of n at some large value of n, let's say m, right. So n should be less than equal to m, and it should be 0 otherwise, right. So in that way we will be able to limit or limit the impulse response, number of samples in the impulse response, right. Now the number of samples would be m, but obviously still it has samples on the other side of the 0 as well, on the left side of the 0 as well, right. Although now it has become finite in length, but still it is symmetrical about origin, right. So the response of this filter, the frequency response of this filter is shown in this graph for omega c equal to 0.4, and you can see that this is the cutoff frequency, omega c equal to 0.4. In the pass band there are some ripples, and in the stop band again there are some ripples which can be observed from this figure. And also you can see that the transition from pass band to low stop band is not abrupt, not like a brick wall, but it is going down gradually, right. It has started at some value before 0.4 here, and after some value of 0.4 it has become 0, not completely 0, but there are certain ripples in the stop band as well. So this is how the practical response of the filter, which is represented by this finite length impulse response of the impulse response function. So now this one in the blue color is h of omega, and this is how the ideal response should look like, which is represented by hd of omega in the red color, right. So you can see that it is impossible for the response to be like this brick wall. We need infinite number of samples, right, which is impossible, which is not possible to design it, but we can actually make it better. H of omega can be made better by increasing the number of samples, right. We can increase the number of coefficients or increase the number of length. M should be large as possible, so that the h of omega here, one in the blue color, should look d of omega. Right, so the truncation is just multiplication by rectangular window function WR of n. WR of n is equal to 1 when n is equal to 0 to m, and it is equal to 0 otherwise. Now let me clear one thing before moving further in this lecture. In some books and even in my previous lecture, the mathematical representation of rectangular window function is equal to 1 when n is equal to 0 to m minus 1, and it is equal to 0 otherwise. So in some books you will find here at 0 to m minus 1, not only in rectangular window function, but the other window function that we are going to discuss in the next slides, right. So sometimes in some books you will find m minus 1 here, and sometimes it is m. Now it depends what value of m you choose, right, because m represents the length of the filter, and when m is 20, the length of the filter is 21, because n starts from 0 to 20, means 21 samples or 21 values, 21, so we call 21 length. So sometimes when the length of the filter is 21, we represent m equal to 21 in some books, and in some books when length of the filter is 21, m is equal to 20, right. So here in this lecture we will assume that when the length of filter is 21, m is equal to 20, right. So already one sample is deducted from m, right. So you can write down n equal to 0 to m. It means length of the filter is m plus 1, right. So you don't have to write down m minus 1. So don't be confused in this. It is just how you choose the value of m. So here we are going to represent m as the length of the filter minus 1, right. So practically the truncated and delayed impulse response is used so that you have a finite length filter and which is also causal, right. So delayed, the amount of delay is equal to m upon 2, right. Whatever the value of m is, half of the samples are on the right side of the 0 and half of the samples are on the left side of the 0. So you have to shift all the half which are on the left side to the right side, right. So delay would be half of the m. After doing shifting and truncation, the resulting filter is causal and finite in length, and therefore it can. So what are the design requirements? That is the fundamental question in while designing the FIR filters. So the design requirements generally falls into these three basic requirements, right. So ideally the filter would be the best one as far as the computations are required. Implementation on a digital computer is concerned, m should be small as possible, because when m is small you need smaller memory, you need smaller onboard computer that can perform these computations in a real time, right. If we have a large value of m, it means you have to perform more computations in real time, you need more powerful processor, right. So obviously m should be as small as possible so that you can implement your filter on cheaper alternatives, right. So that is one thing to consider while designing the FIR filter. Another fundamental requirement is h of omega should be as close as possible to hd of omega. Hd of omega, as you know, is the ideal filter requirement, and h of omega is the practical filter design. So it should be as close as possible. So it means narrow transition band, as I showed you in the previous slides. So when they are close together, the transition band would be narrow, right. You would have a brick wall response, which is ideal requirement, and if we can achieve this practically, then it's a best design. Then flat pass band and stop band. There should be no ripples in the pass band and the stop band, right. These are the three requirements while designing the FIR filters or any other filter, but these requirements are actually conflicting, right. This is the problem. So you have to make a trade-off somewhere, right. So how these designs are conflicting, we are going to perform the detailed analysis in next slides. Then you will understand that where the conflicts come and how you can actually do the trade-off. Now as m is increased, which is the dimension of the window or the length of the filter, right. So as m is increased, transition band gets narrower, but the ripples remain. I am talking about when we are using rectangular window for truncation. So you can see that this is the transition band. Transition band is simply a transition from pass band to the stop band, right. But it's not like a brick wall. It doesn't happen suddenly, but it takes some time. It happens gradually, right. So this transition band, it gets narrower when m is increased, when dimension of the window is increased, or the filter coefficients are increased, right. So here m is 15. When m is increased to 30, to twice, you can see now the transition is somehow sharper as compared to m equal to 15, but the ripples are still there, right. Here we had 3 oscillations in the pass band. Now we have 6 oscillations, twice as much, right. Similarly in the stop band as well, right. So oscillations are still there, right. And if we increase m further from 80 and 120, we can see that the transition band is getting narrower, and when m is equal to 120, it is like a brick wall, but the oscillations or the ripples in the pass band and the stop band are still there, right? In fact, number of oscillations are much higher than the number of oscillations when m is equal to 15, right? So we can say that as m is increased, the transition bands get narrower, but the ripples are still there. The ripples are increasing in number, right? Increasing in their width is decreasing, and probably their peak value is same, but the number of ripples are increasing, right? So increasing m the ripple problem, it is solving the transition problem. And let's see what happens to the magnitude response of the rectangular window function, right? So this figure shows the Fourier transform of the rectangular window. You know that Fourier transform of the rectangular pulse or rectangular function is a sinc function, right? So this figure shows the magnitude response of the Fourier transform or the magnitude of the Fourier transform of rectangular window function, right? So this on the x-axis we have normalized frequency, and we have magnitude on the y-axis, and you can see that we have a sinc type of graph. And now in this graph we have one main lobe, which is this one, which appears at 0, and the width of the main lobe is directly dependent on value of m, right? And we have a side lobe, in fact series of side lobes, but the first side lobe is the highest in peak, right? So we call this peak side lobe. So we have main lobe and we have side lobes, right? So width of the main lobe is dependent on m equal m, and peak side lobe that would depend upon value of other parameters, right, that we are going to discuss. So here you need to understand that this one is the main lobe, and width of the main lobe here directly depends upon m, and we have side lobes, and the first side lobe is basically has the highest peak. So when m is increased, you can see the width of the main lobe is decreasing, right? Width of the main lobe has decreased significantly, but the side lobes are still there, right? In fact, their peak and number of side lobes has increased as m is increased, right? Right, so the width of the transition region between pass band and stop band in h of omega is directly proportional to the main width of the main lobe of WR of omega, right? As we have seen that when m is increasing, the transition band is decreasing as well as the width of the main lobe is decreased, right? So the transition band directly depends upon the width of the main lobe in the frequency response or the magnitude response of the window function, right? Whether it is rectangular or other window functions that we are going to discuss in next slides. So for now we are only discussing our all this discussion based on the rectangular window function, and this would also apply for the other window functions as well. So the first thing is that the width of the transition region is basically dependent on the width of the main lobe of WR of omega, and both depends upon the value of m. As m is increased, the width of the main lobe decreases and the transition band decreases, right? The ripple in the pass band and stop band is dependent on the area under the side lobes, right? So the ripples in the pass band and the stop band is dependent on the area under the side lobes, right? And we have seen in the previous slides that the side lobes are not going anywhere, whatever the value of m we choose, right? They are always there. So for the rectangular window function, that the width of the main lobe decreases as m increases, but the area under the side lobes remains same. So side lobes are always there, whether we increase m or we keep m same, for high values of m or for lower values of m. Therefore, we have seen in the frequency response of the filter in the previous slide that we increased m, the transition band decreased, but the ripples were still there, right? Because side lobes are not going any, they remain unaffected. The area under the side lobes remains same, whatever the value of m we choose. Therefore, the ripples would always be there, but the transition band is decreased when m is increased. So, what is the problem? The problem with this window function is sharp discontinuity in rectangular window. Because it is sharp discontinuity, it is a brick, like a brick wall, right? It is like an ideal response, and because of this sharp truncation, we have oscillations in the pass band and the stop band, which is called the Gibbs phenomena. So, in conclusion, we can say that when we use rectangular window function, there will always be oscillations in the pass band and stop band, right? And but by choosing m wisely, we can actually make the transition band smaller as possible. So, what is the solution of this ripples? The solution for the transition band is that choose higher value of m, right? But as long as we are using window function, we cannot get rid. So, in order to get rid of ripples, we probably need another window function. So, let me just clarify using the example 1 that we solved in last lecture, in which we designed low pass filter having cutoff frequency 0.4 pi with rectangular window function, right? This was the impulse response, right? This impulse response is truncated as well as shifted m upon 2 units on the right, or delayed m upon 2 units, right? So, now in this frequency response, we have m equal to 21, then m equal to 100. So, m equal to 21, you can see one in the blue color, we have oscillations in the pass band as well as we have oscillations in the stop band, and the transition is, it starts before 0.4 and ends after 0.4. But when m is 100, the oscillations are still there, but the transition now is somehow like a brick wall, right? So, increasing the value of m has only solved the problem of transition band using rectangular window functions. So, the oscillations are still there. Now, so what is the solution for these oscillations? Choose another window function, right? Because rectangular window function has a sharp discontinuity, right? So, use window with no abrupt discontinuity in their time domain response, and consequently low side lobes in the frequency response, right? When we have low, we do not have any abrupt discontinuity in the time domain, then in frequency domain there won't be side lobes, right? So, for that we can use another window function which has smooth transition in time domain, right? So, in this case, if we use another rectangular function, another window function which do not have sharp discontinuity, then we can solve the problem of ripples. But obviously, because of the smooth transition in time domain of another window function, we can have a large transition band, right? It is a trade-off. If we use sharp discontinuity window functions, you will have a sharp transition band, but you would have ripples in the pass and stop band. But if you use a smooth transition window function which do not have sharp discontinuity, then you might have no ripples in the pass and stop band, but the transition band would get larger, right? So, it is basically the design trade-off, that how much ripples you need and how much sharp transition you need from pass band to stop band, right? But obviously, you can increase the sharpness of the transition band, or you decrease the or you can decrease the transition band by increasing the of the filter by choosing higher values of m, right? If you remember in the last lecture, in example 2, we use Hamming window for designing the same filter, same low pass filter. Right? So Hamming window is do not have sharp discontinuity. It has smooth transition. Right? So it is from 0 to m equal to 0.54 minus 0.46 cos of 2 pi n upon m. In the last lecture, probably we have m minus 1 here for the same reason that we discussed in the previous slide. Right? So Hamming window do not have a sharp discontinuity, and therefore we expect less number of ripples, but we should expect wider transition band. The impulse response of the filter now would look like this impulse response of the ideal shifted and delayed version and truncated version multiplied by this Hamming window function. So now here we have plotted the frequency response of Hamming window function, and now you can see that the side lobe, the amplitude of the side lobe is very low. They are practically non-existent, right, for same value of m. So we have very small side lobes, and width of the lobe, however, seems greater than the rectangular window function, right. So width of the main lobe is wider than the rectangular window function for the same value of m. However, there are no side lobes, or there are very low amplitude side lobes, right, because of the smoothness in the transition. And if m is increased, you can see that the width of the main lobe has decreased significantly, right, and the side lobe is still there, but has very compare the frequency response of rectangular window function and the Hamming window function. The rectangular window function's frequency response is given in blue color, and Hamming window is in brown color, and m is equal to 15 here. So you can see that the width of the main lobe is greater than the width of the main lobe of rectangular window function. However, there are no side lobes in the Hamming window as compared to the side lobes of rectangular window function, right. So this is again evident that the transition band would be wider in Hamming window, but would be smaller ripples, and in rectangular window function the transition band would be slightly sharper, but it would have larger ripples in pass band and stop band. Now the frequency response of the filter with Hamming window and the rectangular window is compared, and again blue color is the rectangular window function filter and brown color is the Hamming window filter. You can see that the transition from pass band to stop band is taking more time or wider for Hamming window. It starts nearly at 3 pi radians, 0.3 pi radians, and it stops at nearly 0.5 pi radians. And for the rectangular window, it is sharper. But obviously, in rectangular window, you can see a lot of ripples in the pass band and the stop band. And Hamming window, we do not have any ripples in the pass band and stop band, or there are ripples which are not visible, which are very small in size. If we zoom in, probably find some ripples. So comparatively, there are no ripples. So if we increase the number of coefficients or increase the length of the filter, we can have sharper transition band. You can see here in the brown color, when m is equal to 100, we have like a brick wall response and without pass band and stop band ripples, right. So using a different window function, we can achieve the design requirements, right. So although they are conflicting and we might have to do a trade-off, but we can achieve the requirements closer to the ideal requirements. And obviously there are other design constraints involved when you are designing for any practical system, right. when we are designing only theoretically, we'll be worried about the ripples and the transition band. But when we are designing for any practical system, then you have to keep in mind that in which application you are going to implement this, what is the digital computer that is used, and what is the environment, real time environment. Maybe the input signal is changing very quickly, right? So if you have large number of coefficients in the filter, probably will be delay in real time, which is not suitable, right? So there are many design constraints when it comes to the practical realization, but as far as the theoretical realization is concerned, we are only worried about the ripple. Now, specifications necessary for window design method. What are those specifications that we need to keep in mind, right? In order to understand those specifications, we need to understand this figure, we need to understand this graph. This graph actually represents the frequency response of the filter, the low pass filter as a general model, and obviously the low pass filter can be converted into high pass, band pass and band stop. So we start our study, or we start as a with the low pass filter as a model, and then same theory can be applied to other filters as well. So this represents the magnitude response of a low pass filter, a general magnitude response of a low pass filter with cutoff frequency omega c. You can see here, right? And this is the pass band. Here the ripples in the pass band are represented by sigma 1 plus sigma and 1 minus sigma as the maximum peak and the minimum peak. So 1 plus sigma is basically the maximum peak, you can see here, right? And it appears when the transition from pass band to stop band is about to happen, right? So maximum peak here in the pass band is probably the last peak, and maximum peak in the stop band is the first peak, right? So this dotted response, you can see this one dotted line, this represents the ideal filter frequency response. It represented by hd of omega or hd of e power j omega, and h of e power j omega or h of omega is the practical filter response, this one, and delta omega here is basically the width of the transition band, the transition from pass band to stop band, that is represented by delta omega, and the width of the main lobe is represented by delta omega m. The width of the main lobe is basically delta omega m. So this is the frequency response of window function being used, right? And width of the main lobe is represented by delta omega m, and you can see the ripples in the pass band are same as ripple in the stop band, represented by delta, right? So pass band ripples and the stop band ripples are represented by delta here. And now we are going to discuss about some key properties which will be used in designing. Now first key property of window design method is that equal transition bandwidth on both sides of the ideal cutoff frequency, right? So cutoff frequency is omega c, and the transition band, half of the transition is from omega c to pass band, and half of the transition is from omega c to stop band, right? So omega c is actually exactly at the midpoint of the transition band, right? So if you know the upper corner frequency, which is this one, and lower corner frequency, find out omega c by adding upper and lower corner frequency and dividing by 2, which is actually the midpoint of this, right? The second key factor is that the peak approximation error, which is delta, in the pass band and stop band is same for window design method, right? Delta, which is actually the ripples in the pass band and stop band, are same in window design method. The ripples in the pass band and ripples in the stop band are same, they cannot be different, right? The value of lambda here, whatever the value would be same here, right? So the third key property of window design method is that the distance between the maximum peak in the pass band to the maximum peak in the stop band is approximately equal to the width of the main lobe, which is delta omega m, right? So peak approximation error here in the pass band and the peak approximation error in the stop band, the distance between these two points is approximately equal to the width of the main lobe, which is delta omega. Fourth key property is the width of the main lobe is slightly wider than the transition bandwidth. Transition bandwidth is delta omega and width of the main lobe is delta omega m. So you can see here the width of the main lobe is slightly wider than the transition bandwidth. And fifth and the final key property is that peak approximation error, which is represented by delta, is determined by the window shape. It is independent of the filter order, and it is independent of the value of m, as we seen in the previous slides. Increasing or decreasing the m and didn't have any effect on the ripples, but choosing the appropriate window function had, right? So delta, the peak approximation error here, or the delta, which act basically same for pass band and the stop band for windowing design method. It depends on the choice of window function and not the filter order. So the pass band and stop band ripples are often expressed in decibel, and because the magnitude response of the filter is also often represented in decibel. So the pass band ripples in decibel are computed using this equation: 20 log of 1 plus delta p, which is pass band ripple, and stop band attenuation is basically minus 20 log of delta s, which is stop band peak value. Right. In windowing design method, you should keep in mind that delta p is equal to delta s. It is always equal to, because we choose same window, which is applicable to the pass band and the stop band as well. So the peak value in pass band, peak error in the pass band as well as in the stop. Now the other popular window functions which we are going to use are Blackman window, Henning window, Bartlett window. We already use rectangular and Hamming window. Right. So rectangular window function is this one. Right. It is 1 when m is 0 or greater than 0, and it is 0 when m is greater than value of n is greater than m. So it has sharp discontinuity, right, abrupt discontinuity. Other window functions are more or less similar in shape. Other one is Bartlett window, one in the blue color here with the dotted line. Right, it is a triangular window. It is also called triangular window. It has a triangle shape. Then we have Hamming window, which has smooth transition, and Henning window. There is very slight difference between Hamming and Henning window even in the equation. Right, and with Blackman window represented by this shape. Right. Mathematical equations of these windows are given here. Rectangular window represented by this, it is equal to 1 when n is from 0 to m, otherwise it is 0. Bartlett window, also called triangular window, is represented by this equation. And similarly Henning and Hamming, you can see there is only slight difference here. In Henning window we have 0.5 minus 0.5 and cos of this, and in Hamming window we have 0.54 minus 0.46, and this is the equation for Blackman window. And obviously you don't have to memorize these equations, right? Whenever such questions is given in exam, then obviously the formula sheet would be provided to you. You don't have to memorize these, you just have to know or understand how to use these window functions. Now these are the characteristics of these popular window functions. uh, we have 5 columns here. One is the serial number, then window type, then we have peak side lobe amplitude, approximate width of the main lobe, and peak approximation error in decibel, which is delta, right, 20 log of delta or minus 20 log of delta. So in rectangular window function, the peak side amplitude is minus 13 dB and width of the main lobe is 4 pi upon m plus 1, and peak approximation error is minus 21. In Bartlett window, we have peak side lobe amplitude minus 25 dB and slightly less than the rectangular window, and approximate width of the main lobe is 8 pi upon m, and the peak approximation error is minus 25. In Henning window, we have peak side lobe amplitude minus 31 and peak approximation error minus 44. And in Henning window, we have peak side lobe amplitude minus 41 and the peak approximation error minus 53. And the width of the main lobe in Bartlett, Henning, and Henning window is same. However, the peak approximation error is least in Henning window. In Blackman window, we have the peak width of the main lobe 12 pi upon m and peak approximation error minus 74. So we have least error or smallest ripples in Blackman window, and on the other hand, we have highest width of the main lobe in Blackman window as well, 12 pi upon m for the same value of m. For example, m is 1, then Blackman window would have highest width or the largest width of the main lobe, right? But obviously it would have least side lobe amplitude, and that would result in least approximation error, right? So you can choose the window type according to the requirement given to you. Now let us solve few examples to have better understanding about the choice of window function and how the filters are designed, not only the low pass filter but as well as the other types of filters. So first we will start with design of low pass filter having pass band frequency 0.4 pi and the stop band frequency 0.6 pi, which exhibits a minimum attenuation greater than 50 dB in the stop band. Right. So from this table you can decide which window function we need, depending upon the requirement of the ripples. Right. We are given requirement that minimum attenuation at the stop band should be 50 dB. So we can see that Hamming window has stop band attenuation minus 53 dB, which is slightly less than the requirement. Right. So as far as the attenuation is concerned, we can choose Hamming window, which actually suits our requirement. Right. So choosing Hamming window as a window function. So first thing you do in window design method, that choose appropriate window depending upon the requirement that suits your requirement, right? And the window function mainly, a choice of window function mainly depend upon that how many ripples you need and how sharp cutoff is required. So from this Hamming window we can have peak approximation error in a stop band which is slightly greater than 50, which is minus 53 dB, and the width of the main lobe is now 8 pi upon m. Right. Now we'll see what would be the value. The second thing we need to do is to choose the length of the window, approximate the window length. Now window length can be determined by comparing the transition band with the width of the main lobe. In this case it is Hamming window. Right? So width of the Hamming window is equal to 8 pi upon m, and comparing it with the transition band. Transition band is simply a difference between stop band minus pass band. So stop band is 0.6 pi and pass band is 0.5 pi. So transition band is equal to 0.2 pi, and comparing it with 8 pi upon m, m is equal to 40. The length of the filter is 41. Right? So this means that the design filter will be of length 41, that is n equal to 0 to 40. So m is equal to 40, and the window function that we are going to use is the Hamming window. Now find the appropriate ideal filter. So for ideal filter we need to have the cutoff frequency, and as we discussed in previous slide, the cutoff frequency is basically at the midpoint of the stop band frequency and the pass band frequency. So midpoint of the stop band and the pass band frequency is 0.5 pi, so omega c is equal to 0.5 pi. Now the ideal low pass filter is represented by this impulse response. Right? So hd of n is equal to omega c upon pi sine n omega c upon n omega c, which is basically normalized sinc function represented by sinc n omega c upon pi multiplied by omega c upon pi. So now you can actually substitute the value of omega c here. So substituting the value of omega c in hd of n, then we have to shift the ideal response to m upon 2 units, right, in order to make it causal. So after shifting you will get 0.5 sinc n minus m upon 2 upon 2, and after shifting we will truncate it. Truncation is simply multiplication with the Hamming window function, which is given by this equation. So now we have h of n, which is the impulse response of a finite length causal filter. Now we need to substitute the value of m in this equation, and now you have your filter design here. Now you can find out the coefficients of the filter. Total number of coefficients will be 41. So you can find out h of 0 by substituting n equal to 0 in this equation, and similarly n equal to 1 up to 40, and you can find out 41 filter coefficients using this equation. The frequency response of the filter is shown here in this figure, and the magnitude response is now in decibel instead of simple magnitude response. Right? So you can see that in stop band we have maximum peak, which is nearly equal to minus 54 dB, right, as given in the table. So as far as the stop band attenuation is concerned, it fulfills the requirement, right, and value of delta is equal to 0.002. So delta s is 0.002, delta p would also be equal to 0.002, and the cutoff frequency is 0.5. Now we know that stop band and pass band ripples are 0.002. So if we zoom in, now this is the magnitude response of the filter, where magnitude is normal magnitude, it's not in decibel, right? So in decibel the maximum peak was minus 54, and it was visible when the magnitude of the filter was nearly 0, right, because logarithmic of smaller values is large. So during stop band the ripples are visible when magnitude is in decibel, and they are not visible in pass band, right? So here both the values are not in logarithmic, so it's not visible, so we probably have to zoom in. So let us zoom in the pass band of this filter Now you can see there are ripples, and the maximum peak in the ripple is the 0.002, right? Similarly, if you zoom in into the stop band, you will find the ripples in the stop band as well, and the maximum peak in the stop and the ripples in the stop band is also 0.002. Now in example number 4, we have to design a high pass filter. The corner frequencies for the high pass filter are pass band frequency 300 Hz and the stop band frequency 200 Hz. So the pass band starts from 300 Hz, and the transition actually starts from 200 Hz and it reaches to the pass band at 300 Hz. So the difference between FP and FS is basically the width of the transition band, and filter should exhibit the minimum attenuation in the stop band, which is equal to 40 decibel, and we must have the pass band ripples less than 0.2 dB. The sampling frequency is 1200 Hz. So in this example, we have different ripple requirement for the pass band and stop band. So first we need to find out what is the value of delta S and delta P, right? And if the values are different, then obviously we have, because as I told you, in window design methods we have to have same delta value for pass band and the stop band. So we'll choose the value which is minimum of both. So find out the delta P and delta S first. So delta P is 20 log 1 plus delta P. So m dB is given 0.2 dB. So after substituting the value, the delta P came out to be 0.023, and similarly the stop band attenuation delta S can be determined. m dB is given, which is 40 dB, and after so the pass band ripples are 0.023 and stop band ripple is 0.01, right? So that is also called the peak approximation error in the pass band is 0.023 and the peak approximation error in the stop band is 0.01. And as I told you that in the window design method they have to be same, right? So we have to choose the minimum of these two, which is 0.01, right? So the delta S is equal to delta P equal to 0.01. So since it is minimum, so it would fulfill both the requirements. So the peak approximation error is now minus 40 dB. So we have to choose the window function that fits this requirement. And from the table we can see the closer one is Hanning window, right? That is slightly greater attenuation in the stop band, right? Our requirement is attenuation of 40 dB, and here we have 44 dB. So Hanning window is fulfills the requirement from this table. Now we have to choose the window length, and for window length we have to compare the transition band with the width of the main lobe of the Hanning window, right? So width of the Hanning window is again 8 pi upon m, and the transition band width of the transition band is omega p minus omega s. Omega p is 2 pi and fp upon f sample, which is 0.5 pi, and similarly omega s is 0.33 pi. So difference between these two is 0.17 pi, and comparing this value with the width of the main lobe formula of the Hanning window, which is 8 pi upon m equal to 0.17 pi, and from this m came out to be 47, but it is not even value. So nearest even value is 48, so m is equal to 48. Now equation of Hanning window is given here that we can use for the truncation of the impulse response, and now we have to find out the equation or the impulse response of ideal high pass filter, which is given by this equation. And ideal high pass filter is equal to sinc n minus the low pass filter. So now we can actually, first we have to shift this response to m minus upon 2 m upon 2 units to the right side of the 0, and then we have to multiply with this window function, right? But before that we need to find out the cutoff frequency, which is at the midpoint of the transition band. So it is equal to omega s plus omega p. Now we have to delay the ideal impulse response by m upon 2 units and then multiply it with the Hanning window function. So after multiplication and shifting, we have impulse response of the filter given by this equation. Now we have to substitute the values m equal to 48 and omega c equal to 0.15. We have our filter design here. Now you can find out the coefficients of the filter by substituting different values of n starting from 0 to 48. So we have a total number of coefficients 49. So length of the filter is 49 and we have 49 coefficients. Here the magnitude response of the filter is shown. The magnitude response is in decibel, and you can see it is a high pass filter. The cutoff frequency is around 0.4. The maximum attenuation in the stop band is minus 44 decibel, is given in the table, right? So obviously it is greater than the requirement, so it fulfills the requirement, and the ripples in the stop band in the pass band are 0.01. Now in example number 5, we have to design a band pass filter having center frequency 500 Hz and two-sided pass band of 300 Hz, right? So we have center frequency 500 Hz and we have 500 minus 300 Hz to the lower band and 500 plus 300 Hz on the upper band, right? So both low and high transition bands of filter are 100 Hz. So we have transition band at the lower side of 100 Hz and we have transition band of 100 Hz on the upper side, on the upper corner. So stop band attenuation needs to be greater than 60 dB now. The pass band ripple is expected to be less than 0.1 decibel. Assume the sampling frequency is 2000 Hz or 2 kilohertz, right? So first we need to choose the type of window, right? For that we need to find out the values of peak approximation error. So for that you can use these equations, and the peak approximation error in the pass band is 0.01 and peak approximation error in the stop band is 0.001. This is the requirement of the question, and obviously both have to be the same. So we have to choose the value which is a minimum of these two, which is again delta s, which is stop attenuation. So we have to choose the window function that gives the stop band attenuation or peak approximation error in the stop band, which is equal to 6. So from the table you can see is the Blackman window that gives the stop band attenuation greater than 60 dB, which is minus 74. So choosing the Blackman window as our window function here. Now we have to find out the value of m. So a value of m can be determined from this by comparing this to the transition band, right? So 12 pi upon m equal to the width of the transition band. So transition band is 100 Hz, which is given in the question, right? On both sides, 100 Hz on the lower side, 100 Hz on the upper side. So transition band is 100 Hz, which is equal to 0.1 pi, and comparing this with the width of the main lobe of the Blackman window, which is 12 pi upon m. So m came out to be 120. So length of the filter is 121. Now the equation of the Blackman window is given here, and we have to write down the equation for ideal band pass filter, which is the impulse response of ideal band pass filter, which is given by this equation, right, which is high pass filter minus low pass filter, right. So we have omega uc, which is upper cutoff frequency, upon pi sine n omega uc divided by pi, minus omega lc, which is lower cutoff frequency, divided by, and sinc n omega lc divided by pi. So now we can actually, we have to delay this ideal response by m upon 2 units and then multiply it with the Blackman window, right. So we now have the new impulse response, which is practically realizable. Now we need to find out the values of upper cutoff and lower cutoff frequency. We know the value of m, which is 120. We can substitute this value. Now we need to find out the value of upper cutoff and lower cutoff frequencies. Upper cutoff frequency is basically center frequency plus the pass band frequency minus the transition band, multiplied by 2 pi divided by sampling frequency, which came out to be 0.7 pi. And similarly, lower cutoff frequency is center frequency minus pass band frequency and minus the transition band, which came out to be 0.3 pi. So substituting these values into the impulse response, we now have the filter, and we can find out the coefficient of the filter by substituting different values of n. This is the magnitude response of the designed filter, and you can see that the bandwidth of the filter is 0.3 to 0.7, and this one from 0.7 to this some value 0.75 or whatever is the transition band from the upper side, and similarly we have some transition band at the lower side, and the peak approximation error in the top band is minus 74 dB because we have chosen the Blackman window. Alright, so in example number 6, we have to design a notch filter, a band stop filter having corner frequencies 1.5 kHz and 3.5 kHz relative to sampling frequency of 0.0001 seconds. Sorry, not the sampling frequency, but the sampling interval of 0.0001 seconds. Both low and high transition bands of this filter are 500 Hz. The stop band attenuation requirement is 26 dB, and for this the suitable window is the Bartlett window. Using Bartlett window is our window function for this filter, and it has the approximate width of main lobe equal to 8 pi upon. So the finding out the window length by comparing the width of the main lobe with the transition band. So transition band is 500 Hz, which is equal to 0.1 pi. M came out to be 80. So length of the filter is 81. Now the equation of the Bartlett window is given here, and the impulse response of notch filter is given by this equation. Right. Again, you don't have to memorize all these equations. The impulse responses of different filters, the ideal filters, and the equation of the window functions, they would be given to you in examination with the formula sheet. You don't have to memorize these equations. So now we have to shift this or delay this impulse response by m upon 2 units, then we can multiply it with the window function. So shifting this by m upon 2 unit and then multiplying it with the Bartlett window function, we have the impulse response of the filter. Now we have to substitute the values m equal to 80 and upper cutoff frequency and lower cutoff frequency values. We have this notch filter impulse response of the notch filter here, and you can find out the coefficient of the filter by substituting different values of n. So this is the magnitude response of the filter, and you can see it has a stop band between 0.3 and 0.6 pi, and since it is a notch filter, it is suppressing all the frequency contents that falls between 0.3 and 0.6, It has maximum attenuation between 0.3 and 0.6, and other than that all the frequencies. Now this is a simple exercise problem in which we have to design a low pass filter according to this given specification. The pass band and stop band ripple requirement is given, and the pass band and the stop band frequency is given, right? So you have to design a low pass FIR filter. Another exercise problem in which you have to design a band pass digital FIR filter. The band edges are given, which are 1.5 and 3.5, and the sampling interval is 0.0002 seconds, and stop band attenuation should be as minimum as possible. So Blackman window actually gives the minimum attenuation, so you probably have to choose that one for this particular exact exercise problem. Then in exercise problem 3, you have to design an FIR notch filter that suppress the power line frequency noise. So power line frequency is basically 50 Hz from an ECG signal. So corner frequencies are 40 and 60 Hz relative to sampling interval of 0.005 seconds. Both low and high transition bands of the filter are 5 Hz. So stop band attenuation need to be greater than 50 dB. So you have to design FIR notch filter for. So that is end of the lecture, and I hope you have understood many of the aspects, and if you have any difficulty you can send me an email, and thank you very much for listening.